All right, everybody, hopefully you can hear me okay. Question is, anybody out there ever had me record a talk of them? Because I want you behind that, so I'm going to run back and forth, and I can try you on tracing you with the camera for a change. I just want to see how that feels. Actually, I'm probably not going to move too far. I just wanted to make a bad joke. All right. Today's talk is EMP, yeah, you know me. Apologies to Naughty by Nature, subtitled Naughty by Nuke. Anybody under the age of 30 probably does not get that joke, but I'll accept that. My name is Adrian Crenshaw. I run a website called IronGeek.com. Please come visit. The videos for this website will be up there. Sorry, the videos from this conference will be on that website rather shortly, and some of them already are. I have an interest in InfoSec education. I don't know everything. I'm just a geek with time on my hands. I may get some things wrong, so please let me know. We'll have some discussion hopefully after the talk. And I'm an irregular on the InfoSec Daily podcast, usually on Thursday evening. And I'm also a senior information security engineer at a Fortune 1000 company. Not mentioning who I work for, but if you're looking for EMP, possibly EMP protective safe, we might be able to hook you up because it's a big metal box, and generally as long as you have a nice conductive surface all the way around touching inside, you should be okay. Just make sure you insulate the inside. But we'll talk about that later, possibility. Okay, also a co-founder of DerbyCon. All right, what is EMP? EMP stands for electromagnetic pulse. So essentially what we have is a power burst of radio waves and quickly changing electromagnetic fields that can cause problems for certain types of technology. It has the effect of inducing currents into what it hits. So essentially it can burn them out or cause interference when it induces these currents. If you all were listening around for some of Larry's talk, you understand maybe a little bit about how radio works and with the antenna and how does microscopic amounts of current being induced into those antennas, which then get amplified and filtered and looked at to be able to pull out the actual signal. Well, an EMP is very much like a radio wave, or it is a radio wave, on a very wide bandwidth and a lot more kilovolts per meter. So long antenna runs, for certain wavelengths, you have to tune it for the right thing. And that's another thing that's going to come up with EMP here shortly, is there's a lot of unknowns and a lot of, will this break or will it not? We don't know. But you get the same effect that you have in the antenna, except you have it in any kind of conductor. And when you start inducing that kind of current into various things that weren't designed to take it, bad things happen. An earlier term for EMP from the British was radio flash. And I'll explain a little bit about that here in a second as well. So why did I select this topic? I don't consider myself a prepper or a survivalist, but I did collect a lot of Powell and Press books as a kid. I was an odd kid, and either odd or adult, I imagine. I like the smell of fried electronics as long as they're not mine. And truth be told, I even like the smell of my own fried electronics from time to time. It's just soothing. I also like the smell of solder, which might explain some problems I have. I'm using the lead-free stuff, I think. And there's a lot of scaremongering videos out there, and a lot of justify or not, there's very little science in the videos I've seen. So I've tried to understand this as best I can and pass this information along. It also fit the theme. They told me, well, we got kind of a prepper theme going on, and so what you going to do? I'm like, well, I'm into electronics, and I'm kind of interested in EMP effects, so let me do some research on it. And so keep in mind that this is like a 2 or 3 week period I just boned up on the information, so I could get some stuff wrong. Another reason that I want to do this is there's a lot of signal to noise out there when you start looking up information on EMP. You start reading stuff, and people will speak with authority about subjects they don't necessarily know about, which is something I hope I'm not doing here. I try to find more authoritative research. You do a search for EMP, you're going to find a lot of survivalist forums, and that runs the gamut. I'm not trying to bash on the survivalists or preppers, but there's some people who think there's effects that aren't necessarily there, and I'll give you some illustrations of that in a bit. I use the Google operator site for mil and site for gov to try to find just gov and mil sites for the most part, but I've also found some other useful resources on the web that weren't necessarily government related. Keep in mind there's a lot of practical limitations on what we've tested and what we've done. Radio waves do weird things. You ever been listening to a radio or TV, or you've been setting up your Wi-Fi network, and you notice this one little spot in the house, I can get a connection. Over here, I can't. And you don't understand why that is. There's all sorts of weird things that happen with polarity, multipath, where the signal's strong, where you have conductors in the wall, all sorts of things that can screw up radio rates. And it's hard to say what will happen when. Also, a lot of the tests I have found information on was stuff that was done during the Cold War. So whether or not modern electronics are as susceptible, more susceptible, I'm going to guess more susceptible, it's kind of varying. Because there's actually, well, there's two opposing forces there. For some of the stuff I'm going to be talking about later on, long conductors, actually you're going to have more current induced into those, but our electronics are getting smaller. However, as our electronics get smaller, various junctions inside of semiconductors have also gotten smaller and, accordingly, smaller and easier to blow out. And so you ask, when was the testing done and where was it done? Also, it depends on the audience. Some of the stuff I've read apparently links off to classified information, which I don't have access to, and some of it was written for very much a layman who has no electronics experience, and some of the stuff is written for people who are physicists. I'm neither. I have an associate in electronics. I understand the basics of electronics, but I didn't find a whole lot of stuff in that middle ground. And so I'm not an expert, so take what I'm about to say with a huge grain of salt. I'm going to say I understand a lot. And when I say I understand, I don't mean the same way a lawyer does. When a lawyer says I understand, they mean, well, I don't want to be caught lying to you later. So I'll say it was a misunderstanding. It was what my understanding was. Now, when I say I understand, this is the best I understand what I read, and I'm trying to repeat it to you. However, if nothing else, I get enough terms out there and some general concepts to where if you're interested, you can research it more yourself. Now, I was talking about misinformation out there. I found these two great examples on, I believe it was Yahoo Answers. And someone was asking about protection from EMP, and one person says, an electromagnetic pulse would short out any electronics, and there is not protection from it. BS on both parts. It's not really shorting them out. It might be burning them out. It might be inducing currents that cause problems. I suppose if you melt down the right component, well, I don't know if you're going to melt it. I suppose there's possibilities of shorts in certain situations, but that's not really an accurate way of putting it. And an EMP reverse magnetizes everything and fries the circuits because of overheating. That's like one of these free energy people kind of talk. It's like, let's throw some pseudoscientific terms out there, well, scientific terms, but not used in an appropriate way, just to confuse matters. Then there's a second one who says, electromagnetic pulses are only currently concerned if you think you're going to get struck by a nuclear weapon of some sort. Was that? Oh, yeah, well. If you're close enough to be affected by the EMP shock wave, shock wave is a bad term, then frying your electronics is the least of your problems. Not true. You can be affected by the EMP without being hit by the physical shock wave. Depending on how concerned you are about nuclear attack, I would just move to a place less likely to be a direct target. May or may not be an option. But there's a lot of scientific misunderstanding of exactly what EMP does and why. And let's go with some basics. We talked a little bit, well, actually, you will hear from Larry's talk. He was talking about some people going out and testing whether or not the trash can was EMP-proof by taking a 12-volt car battery and walking around it, sparking it. It's still a shitty test for EMP. But technically, it's not exactly wrong. It's just kind of like testing your bulletproof vest with a pellet gun. You are causing an electromagnetic pulse when you do that spark. I mean, any kind of thing that throws out radio waves could technically sort of be an EMP. Actually, some of the earliest communications we did for us radio was a spark gap, where essentially you cause a spark, and over a wide spectrum, you have this noise that goes out there, you can pick it up. If you go just, it really sucks as far as the amount of bandwidth you use. I mean, literally, as far as all the frequencies you're throwing it out there. So, for worldwide communications, a whole lot of people communicating, it would suck, but you could do Morse code with this. You've also seen this the same effect. If you have an analog TV, you ever ran the vacuum cleaner or motorized something or other, or and you notice these sparkling happening on the TV, that is an example of little electromagnetic pulses in a way, or radio waves screwing around with your TV set. Anytime there's a quickly moving current like that, you're going to have some of those kind of effects. Maybe go up to a radio, go take a 9-volt battery, rake a piece of metal across the front of it, you should see some similar effects. Now, we'll talk a little bit about inducing current. Now, there's near field and far field effects, which I'll get into a little bit here in a second, and I don't fully understand them, and hopefully someone who's bigger in the ham can explain it to me later on. But essentially, you can induce a current into a wire by just having a moving magnetic field across it, or the magnetic field has to be changing. Also, a wire in itself will have a magnetic field around it because of the current going through it. Right here, you see something that's following, and possibly poorly, the right-hand rule. And you know what? I just totally realized I think I messed that up backwards. All right, let me give you an explanation of the right-hand rule and also something about conventional versus real current flow. I screwed that one up, but then again, the picture's so bad you may not be able to tell if it wasn't the fact I told you. Conventional current flow is, it was assumed everything came out of the negative terminal and into the positive, but it's actually the electrons that are really moving. So everything's technically, it's the electrons flowing from the positive to the negative terminal. So when I drew this image, I was doing the right-hand rule, thinking current going that way. I should have been doing current going that way. Here's the right-hand rule, and it makes physics students and people who do electronics and radio look silly. It's its main point. But you take your finger around a conductor. Let's say that was the positive side of the conductor. It's conducting electricity. If I wrap my hand around it and point my thumb in the direction of conventional current flow towards the plus, my fingers wrap around it, and my north pole lines of magnetic flux point towards the south pole, the other magnet's south pole. So actually, the Earth's geographic north pole is actually a magnetic south pole, if I'm following this correct. Correct me if I get this wrong. But the right-hand rule is basically to show how you organize the magnetic waves coming off versus conventional current flow. And you also work somewhat the opposite way for inducing a current back into a conductor. And like I said, it really makes people look silly when they try and do this and figure out, okay, it's going this way and that way. And as I was laying out these slides trying to figure out which way would the magnetic waves actually be doing, you see me doing this in the air a lot. And you see that last one, I got it wrong. There's near field and far field effects, and I'd love to talk to someone later on about the explanation of this. The best I can say is when you're nearby something, things act more as the individual components as far as electric fields or magnetic fields. And we think of like a transformer where one coil is next to the other coil and induces a magnetic, or the magnetism from one induces a current in the other. That's closer to near field effects. When you start getting out further away, you have the radiated current, the radiated waves, the radio waves, in the far field. And of course, you have it all in the middle as well, but the types of effects you get are different. And the amount of energy you actually put out there is different. Everybody knows the inverse square law, where the further out you go, every time you double the distance, you only get a quarter of the power. It's actually the inverse cube rule for near field effects. And also your little near field communications devices, like I have actually I'm about to get it right now. If you don't mind, I need to get into my vest real quick. I better get it ahead of time because I'll be needing it here in a bit. Like I have near field communications in my tablet here, and it induces a current into, let's say, what's basically an RFID card, or it sends the signal using the same kind of communications and gets back a message. For instance, I carry around a card with me, and this card has some weird stuff I need to show you later on. I carry around an RFID card with me. I'll explain the tinfoil here in a bit. This RFID card I've preloaded with a bunch of things. Like near field communications is based around RFID. If you've got the right equipment, you got the right type of card, there's all sorts of standards. There is interoperability there. So I got this RFID card that I wrote to with my Nexus tablet. And what I carry around on it is a bunch of strings, like I have the ICARS test string for testing out antivirus. I put that on there. I figured, what if someone scans this and it goes into a database, and the database is seen as having been infected by malware and gets deleted? This idea, I have like a all 1 = 1 on here, and I have a XSS injection in here. But I thought it being, who the hell thinks to sanitize things like RFID cards or barcodes for that matter? I spent a lot of time thinking about how to screw things up. But anyway, I can read that with this device. And essentially, there's conductors in there, and not only does it get the radio signal going on, but I have to do it later because this is booting. It induces a current when I try to read it in the card, and then it can communicate it with it over radio. In many ways, it's acting like a little bitty transformer. All right, before I get out in the far field, we're talking about self-propagating radio waves. So you think of the electric field and the magnetic field, and it keeps things going. And you have something called polarity, which, if I understand, polarity is generally oriented towards the same direction as like your antenna. So you have, if you're going up and down with an antenna, generally you have vertical polarity. If you are going across, it's horizontal polarity. So what we got here is a great big old horizontal antenna. So a horizontal polarity, electric fields going out this way, magnetic fields going out that way. And you thought I looked silly when I was doing the right-hand rule. Okay, now, I did a little bit of a science background on you. which may have bored the living hell out of you, but I thought I should cover it because it may be necessary to understand things I'm going to talk about later on. Now, a bit of history. Apparently, EMP was expected by Enrico Fermi, and this was back for the Trinity test back in July 16, 1945. So they actually did shield equipment in anticipation that it might be a problem. However, they still had some records lost because of spurious pickup. So basically, they got frequencies coming in like, well, that data doesn't look right. Because think about if you're recording something on, like, I don't know, magnetic tape or whatever, and all of a sudden, a big magnetic field wipes it. That's a type of spurious pickup. Or you're expecting to capture this certain amount of radio waves, and all of a sudden, it's overwhelmed by a hell of a lot more, and it pegs your meter. That's an issue. And I'll talk a little bit more about pegging the meter here in a second. Greater interest, though, came about this during the Starfish Prime test. That's what I envisioned it looking like. That should have been the mascot. Anyway, Starfish Prime was part of the whole Fishbowl series of high-altitude tests. And so this particular one of the series, Starfish Prime, was done on July 9th, 1962. And it took a 1.4 megaton. I don't know why that popped up now, but OK. I'm so glad it's giving me very innocuous names as opposed to what they would actually be. Anyway, they took a 1.4 megaton bomb, and it was a W-49 thermonuclear warhead, took it up 250 miles, 400 kilometers, and blasted off about 19 miles southwest of a place called Johnston Island in the South Pacific. They were expecting some EMP, in my understanding. They had things calibrated for maybe certain expectations. And when I say calibrated, think about back then, you wouldn't really have the digital multimeters like we have now. So you used to have pegging the scale. You used to have all your multimeters having little meters with a moving needle. Well, when you peg it, you put too much into it, and you could possibly break your needle. Well, let's just say the EMP effects was a little greater than they expected. Drove instruments off the scale, presumably because the expectations were a lot lower. And it damaged electrical systems like 898 miles away on Hawaii. So like 300 streetlights get blown out, telephone microwave link gets damaged, and sets off tons of burglar alarms apparently also. Further tests in Operation Fishbowl series gave more data on EMP effects, though eventually there was some, high-altitude test ban. So there's probably could be more information out there, but some treaties stop us from testing, which may be a good thing, may not be a good thing. I don't really have an opinion on it. I haven't researched that part enough. But there has been some studies of a high-altitude EMP pulses caused by nuclear devices. Now, we start talking about EMP, especially HEMP, high altitude electromagnetic pulse, not the other type of HEMP some of you all might be thinking of. It comes in three parts. Generally, we have the very short initial burst that has induces really high currents in conductors. And it's like, boom, it's there, and it's very powerful, and it's all sorts of frequencies, and just very short effect. It comes so fast that some surge protection can't handle it. E2 is a little bit more akin to having a lightning strike go off next to you. Remember I was talking about spark gaps causing EMP of a sort, causing wide spectrum radio waves to go out? Well, a lightning strike is basically one big spark gap. So a lot of stuff is probably somewhat hardened against the effects of E2. This comes about a little bit later. Unfortunately, if someone's blown out because of E1, E2 might have a little bit more effect. Then E3 is another interesting one. And if you ever heard of a geomagnetic storm, geomagnetic storms are essentially like E3. E3 is essentially when your fireball goes up or it affects the nuclear weapon, it screws around with the how well magnetic fields go through that part of the atmosphere. And so you see it pushing the Earth's magnetic fields out of the way, and as it dissipates, coming back. Well, you have a moving magnetic wave there, and you can induce current. This is especially a problem, apparently, in very long conductors. So think like your telephone system, maybe that, your power lines, things like that. Now let's talk about volts per meter. Here's the big issue. I already told you before, like EMP is essentially radio, but they're a little bit different. For instance, I have some ballparks I got out of FEMA doc, and some EMP estimates would be like 100 volts per meter on a ground burst. We'll talk more about that a little later. I think I've seen estimates of the upper limit of HEMP conventionally being about 50,000 volts per meter. But to put this in perspective, radar, which you can get, burns off of a radar dish, if I'm not mistaken, if you get too close to the wrong effect, that's 200 volts per meter. Way, way lower. Let's talk about radio communications. 10 volts per meter. Let's talk about metropolitan noise, just caused by, well, once again, people running their vacuum cleaners and so forth. 0.1 volts per meter. And this is the amount of voltage you get across like a 1 meter conductor. So keep in mind, things get a little bit more confusing when you talk about the orientation of the wire and so forth. So predicting what will and won't get blown up, like I said, can be difficult. But I'm just trying to explain mostly the science behind this. All right, we'll talk a little bit about a couple different types of blasts. But one of the first I want to talk about is ground burst. This is someone blows up the bomb on the ground or very close to it. I think they sometimes refer to it as a SREMP, a source region EMP. But essentially, it's blown up on the ground. But for various reasons, while you might have a very high electromagnetic pulse nearby, it doesn't get the range the HEMP does. So for a small area, you're going to have more of an effect. But the thing the guy said on Yahoo Answers was somewhat true for ground burst. If you're close enough to worry about the EMP, you may also have other bigger concerns, but it does go out a good way still. So you get far enough away, though, you'll survive the blast, but EMP may still screw with you. There's also the burst locations. The main ones we're going to deal with are these first two. We have surface burst or near surface burst, and it's over a geographic limited area. EMP is an issue, but other effects probably take precedence. And air density may limit range, though that may not be accurate. How do I put it this way? I find various reports and people say things, and I'm not sure that's actually accurate. The idea being that the density of the air causes, and I'll talk about Compton scattering here in a bit, the electrons not to be able to move as far, so you don't get as much of a charge separation. Though I don't know if that's an actual true statement. Regardless, the distance you cover with a surface burst is not nearly so much. As you can see, we're going out here. Distance from ground zero in miles. Once you get out to 13 miles, you see how it's dropped significantly. The HEMP can go a lot further. All right, HEMP, a little different. You got to get above that 30-kilometer range. Some are way further up than that. That 30 kilometers is kind of important because apparently the sweet spot for causing this Compton effect is like 20 kilometers to 40 kilometers. And I've seen different versions of that. They say that conventionally the saturation, basically the highest numbers of volts per meter you can get is about 50,000. Though my understanding, there's supposedly ways people can optimize to get beyond that. And a 50-kilometer burst, 500 kilometers above the continental United States, in theory it could cover all the continental United States. So flying a huge region. So this is why HEMP is so interesting, because with a smaller bomb even, you can get a very large effect over a large area. And one of the reasons some people would be interested in attacking first world countries with this is generally we have better technology than other countries. And if you take out someone's radio communications, that causes all sorts of problems for instant response, military coordination. What is it called? A force multiplier, I believe, is the term they use. So yeah, that can be bad. Air burst, it's a little different. It's somewhere in between. My understanding, World War II, when we dropped the bomb on Japan, but those were both air bursts, so I understand. Basically, you set it off somewhere between, and by the way, these figures are all relative. There might be some room for debate on how high each one has to be, and there's ones that kind of fall into the different layers. But let's say 100 to 1,000 meters, but maybe below 30 kilometers. I've seen different versions of that. It's not interesting for EMP, and I'll cover that in a second. It's still interesting for destroying stuff because of how much range you want to cover, and if you want to avoid as much fallout, having an air burst, my understanding, if you want to blow shit over but not cause as much fallout, is actually better than ground burst. If you're trying to take out a bunker, my understanding, ground burst is better. Not that I'm regularly planning, a nuclear attack at any time. I'm talking to the United Nations about them letting me have a treaty where I can have my own nuclear weapons in Northern Indiana, but so far they just haven't responded to my emails. I don't know what the deal is. Hello, Trussery. Dude, I've been on a list for a while. All right, shrimp. Source region EMP. This is essentially your service burst. And I'll be talking a little bit about Compton scattering, Compton effects, and so forth. That's the source region. That's where the charge separation happens. That's where the electrons go over here, and the ions stay over here that are positively charged. HEMP is high altitude EMP. MHD EMP, that's Thank you. Say that louder.
Magnetohydrodynamics.
I'm glad you said it. This is caused by Earth's shifting magnetic fields. So that's that effect I talked about earlier, where like the fireball happens. I'm trying to think of the correct term. Magnetic conductivity is not quite the right term, but magnetic permeability, I believe, maybe, of the Earth's atmosphere gets changed by the bomb going off, and the magnetic fields go around it kind of, then come back. Well, you have a changing magnetic field, so you can induce current that way. The SIGIMP, which is basically gammas or X-rays, are going to hit the outside of, let's say, well, the shuttle, if you had one up there, or satellites would be a big issue. And because those hitting the outside of the ship, or the satellite, induce currents inside of it. And you got to remember some of these, well, I gave you the list for covering the continents of the United States. That was, what, 500 kilometers? I believe the International Space Station is at 300-something kilometers. And there's some satellites in low Earth orbit that would, be within that range. So that's an issue if someone wants to take out communication satellites. They can take out these satellites and some stuff on the ground. And there's also NEP, non-nuclear EMP, which we'll talk about here in a bit. Sounds like science project time. All right, we're going to talk about the first type. And I got busy with the animations. And, pardon me, I may have been drinking a little vodka while I was putting together these animations, but we'll see how they turn out. All right, first of all, we have the ground boost. Boom! Well, that causes an effect. You have the ground absorbing some of the gamma rays as they go down. Gamma rays, in my understanding, are basically very high-powered X-rays, very powerful ionizing radiation. And because of that, it knocks electrons out of the air. And because the air has electrons knocked out of it and move away, you have a charge separation, and you have a movement of current. We talked before, movement of current makes those radio waves. Well, at this point, we have a dipole of sorts. And the dipole in this case is mostly upwards because the ground absorbs some of the gamma, so you don't get as much electrons going that way. The Earth has a return path through it for electrons. And remember I was doing that right-hand rule before? Well, that is because, let's say the electrons are moving this way. Well, actually, I should be going with positive flow, so it would actually be this way, and this would be pointing out. So these little dots is the magnetic field pointing out and kind of around, but this is producing that magnetic field outwards. And that was at like 100, depending on what you blow up, I suppose, 100,000 kilovolts per meter. Now talk about airburst. Airbursts, not as interesting from EMP effects. Essentially, you have a much more even spread of the gamma rays. So you have that Compton scattering where it knocks the electrons out of molecules in the air. You have this current. And because of differences in atmospheric distance, you still get some EMP effects. The idea being is, since you have it happening in the middle of the air, almost as many electrons get knocked this way, that way, that way, that way, that way, as it do straight up. And so it kind of balances itself out. And you want to talk about looking silly while trying to do the right-hand rule on this. I was going, okay, if this one's going this way, 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 I was trying to figure out how it goes. And there's probably a few times where I screwed it up because I keep doing, when I went to electronics school, where we basically used actual electron flow, but doing the right-hand rule of current flow messes with my mind a little bit. But anyway, because it kind of equals out to a degree, it's not as important as far as EMP from my understanding, but you do have a slight vertical dipole going on, so you do still get some EMP, because there is differences in the density of air. It's going to be less dense as you go up, so the electrons can flow further up. Now let's talk about the interesting one. We'll talk about chain of events for E1 and E2 for HEMP, high altitude. So you blow something up, way up in the atmosphere, let's say above 40 kilometers. Gamma rays caused by the detonation go out. I call them little blue bubbles. The earlier ones were green because, Incredible Hulk. Knock electrons out of the atmosphere, let's say in the source region, like 20 to 40 kilometers altitude, and in a mostly down direction. These get caught up in Earth's magnetic field, and it causes them to change direction going around the Earth's magnetic field, and you have an EMP blast that goes down. And people talk about distance. My understanding as far as the inverse square rule, because EMP is coming from such a large region, it's not like being radiated by a point source of light. So distance doesn't matter quite as much. It more matters altitude and what you can see via line of sight. So gamma ray diffusion and other effects cause the E2. That was that effect that's a little bit more like lightning, not quite as bad as far as quick rise times and so forth, but can still screw up things. But it's easy to prepare for. Now that brings us to E3. And if you're just worried about geomagnetic storms, which we'll talk about a little bit later, my understanding is they're basically characterized by E3. Essentially, you have the blast going off, and this messes around with the magnetic permeability. There we go. And causes the Earth's magnetic field to kind of move out of the way and then come back. So we have like long conductors, like, well, power systems. This could possibly overwhelm them. And another issue with EMP is the spread spectrum over which it's over. Like here, I think this is for the most of the E1 effect, perhaps. But you see that large range. We're covering, electric power, audio, all the radio frequencies that hand people are normally going to be messing around with, UHF radar, all the way up till we get to like visible light, pretty much. So filtering for just this stuff could be an issue. And it's going to cause lots of interference. Now, while the EMP is going off, of course, your radio is going to be hosed regardless. You're not going to be able to get any intelligence out of that. Hopefully, it's going to survive depending on where you store it. And we'll talk about that here in a bit. And Larry's probably done more prepping on that than I have. I've been mostly doing research on the scientific effects of it and seeing if I can explain it with pretty PowerPoint animations. All right. Latitude and altitude make a big difference. Like I said, if you do it somewhere in the middle, you don't necessarily get that same charge separation. You do it high enough, though, you can cover a huge, huge area. Let's go ahead and go to the next one. Okay, altitude, yield, all sorts of things matter in EMP production factors. Like people go, well, it's kind of hard for a third world nation to put together, like, say, a 1.4 megaton bomb. You don't really necessarily need that. There's other things that are important. More important than yield. That was a thermonuclear device, which my understanding, I think the Starfish Prime was an H-bomb. My understanding, because of how it works, it doesn't actually have that prompt gamma burst like some others do. And if you do the series of events a little bit wrong, you can have a problem where let's say it heats up the area first, and the gamma rays really don't get a chance to, it changes the conductivity of that area, and you don't really get that electron flow. So you don't necessarily, one of the more powerful thermonuclear devices may not necessarily have more EMP effect because of how it pre-ionizes the air. Yield and construction makes a difference, like whether or not the explosive is gamma ray, well, let's say translucent, how you shield it, how you construct the bomb. Distance from destination makes a difference. The geography of it, let's say where a mountain is and so forth, because we're talking about line of sight. And magnetic field strength over where it happens in the world. Like I'll be showing you a horseshoe shape here shortly that I'm trying to explain it. But let's talk a little bit about other ways someone could put together a bomb. Now, my understanding from Starfish Prime, Starfish Prime test, that was a very inefficient bomb for generating EMP, but yet it had huge effects. And if it had been over the continent of the United States, it would have been probably possibly. So that was a 1.4 megaton bomb, but only like 0.1% of its prompt gamma yield was there. So that of its total power. So basically for EMP effect, let's call it 1.4 kilotons as far as EMP effect is concerned. Well, you can optimize these, and some nukes have, let's say, 0.5 for the nuke's energy and prompt gamma yield. So let's say we take a 500 kiloton nuke, but make it and design it in such a way that it may not be as powerful as far as measured versus TNT, if I'm not mistaken. May not as powerful in the pure explosive force, but it's optimized for EMP. Well, in that case, we take a 500 kiloton and optimize it for that 0.5%. We could get 2.5 kilotons value for the EMP effect. So from a smaller bomb, still get more effect than that 1.4 megaton bomb. My understanding, the pre-ionization caused by a thermonuclear device, depending on its design, can cause that Compton effect not to happen as severely, which reduces your EMP. So there's all sorts of things that can be done to optimize. In some cases, my understanding, primitive fission weapons are actually more efficient for creating EMP blasts than more modern weapons. I'm tripping on stuff. Let's put that back in there. Oh, is that still recording okay? Is it audio level all right? When I speak with audio? Cool. We had the horseshoe effect. Because of how the Earth's magnetic fields work, things get bent back in a slightly different way. So it's not like it's a circular, it's not like a flashlight holding it down in the center is like the brightest and it kind of gets dimmer outside, you have a weird horseshoe effect depending on where the blast happens. That's because of how the Earth's magnetic field is shaped and where it's throwing stuff down. But I believe this one was a picture for like a detonation blast 400 kilometers above the Earth. I'm not sure what the megatonnage on it was or the construction. But there's also the entry points for these signals to get in. So it's direct, let's say through holes. Like you have, well, we were talking about building boxes. Like let's go back to the safe example. Well, some safes would still have a little bit of a lip around there. The idea is not to let a human get in, but not necessarily to make it airtight, or even more than airtight. So something can still get in. Or let's take ammo cans. Ammo cans, and the wavelength, I suppose, would still have to be very, very small and get, I have to imagine, reflected around some. But an ammo can is not a perfect conductor all the way around because of that metal, that paint. So you put that lid on there, yeah, things could possibly get in. There's also induced current that comes in. Let's say you have a fairly well-shielded metal box. You still got to get power into it. If it's a building, you may still have to have antennas and radios out there to get stuff in. There's network cables running various places, telephone wire, other types of cables, plumbing. So this is all stuff that current can get induced in and get into a facility. Now, there's a couple different damage types we'll talk about. There's functional damage, and this is basically overload. You hit something with so much voltage, it heats up and fries. Blue smoke, it's gone. By the way, everybody knows that electrons are magic and it operates on blue smoke. And when the blue smoke escapes, it's like a genie. They're no longer magic, so no longer work. Okay, just so you know. Actually, if you want to understand basics of electronics, there's a book called, oh, great. Electrons don't exist, there's no such thing as electrons. Well, this guy explains all of, well, most electromagnetic theory you need to know in form of like these little hippie greenie guys who just want to go party with these greenie girls, who I guess are the positive charges. And it explains everything like from resistors to capacitors and everything as little greenie guys trying to go get to the party. It's really a cool book if you ever can find it. Anyway, there's also operational damage. And this is like a little bit of current induced on, well, let's say you have an OR gate or something like that in a circuit. If you induce, let's say an AND gate, normally you only have one high and the other one's low, but if that current induced by EMP makes the other one high, you just change the logic at that gate unintentionally. So imagine this hitting like a CPU, all sorts of weird effects happen. And they do try to compensate for this kind of thing in, well, for other types of radiation possibly causing problems in space. If you look at the cost of some of the CPUs in space versus the amount of performance you get, but they don't use the general commercial off-the-shelf stuff that we use. It's not nearly as fast, but the idea is to make it robust for not so happy environments. So that's like two types of damage you can cause. Operational damage is just going to be that short-term thing, but it can still screw up the equipment, cause things to crash, and so forth. Now, let's talk about optimizing for a super EMP nuke. Can you optimize a nuclear bomb to have more of an effect? And I covered a bit of this earlier. If you're going to reduce that ionization from heat in the initial part and make the case an explosive gamma transparent and produce as much gamma as quickly as possible, you could optimize for a greater EMP effect. And I've seen it said that the saturation for conventional nuke would be like that 50,000 kilovolts per meter. My understanding there's ways of getting around that, getting over that. That brings us to non-nuclear EMP. Actually, I never hear anybody refer to it as EMP, but I think it's a cool term because you can have that little EMP guy there and a little goblin thing. I think that'd be a cool logo for people doing research on this. My brain goes weird places sometimes. Oh yes, actually that'd be kind of cool. Instead of a daemon, there would be an imp. I don't know what he'd look like. Maybe we should just discuss this later on. Anyway, think of an EMP device, but without the nasty nuclear side effects like normal ionizing radiation. And because keep in mind, EMP, and I think I had this on a previous slide, but I may have covered it. Why would someone want to use one of these EMP devices? Well, first of all, I talked a little bit about force multiplier, and if your opponent's more technologically advanced than you are as far as communication systems and organization and computerization, if you could take that out, that makes you somewhat, it gives you more of an advantage because they're more reliant on it than you are. Also, as far as effects on electrical systems, if you're not dropping nukes on people, nukes have a very bad reputation. You also have radiation I was mentioning before, the fallout, so forth. You can cause that without, if you cause an EMP effect of taking out technology without causing those, you might have less political ramifications. For instance, generally when EMP goes off, it's not going to affect human beings directly. As opposed to certain things like, let's say you have a pacemaker that you're in for a bad day. But generally speaking, in EMP, it's not ionizing radiation. It's not going to kill most human beings unless, of course, you happen to be, I suppose if you're on a metal plate here and a metal plate here and you're standing on it and there's like a big old like E3 wave going through and it conducts through you and you become the part of the circuit, that'd be bad for you. And, you know, hospitals going out and not being able to service people will die that way. But generally speaking, EMP doesn't cause a direct death. And less direct deaths might mean less political ramifications, which means someone might be more willing to do it. There's various ways of creating an EMP effect without actually setting off a nuke. I believe they usually involve a lot of capacitors charged in parallel, then discharged in series, like a Marx generator. You can go out and online and find people generating these making these little Marx generators, and those are used to feed other devices. And you have that electrical blast that causes that wide spectrum of radio waves, and they use that for testing various types of equipment. Like I've seen on one particular show where someone was using some equipment like that to test out computer cabinets, or in this case, you see someone's testing out a plane. I'm trying to remember. Yeah, that one's the Sandia trestle. It's using for testing a plane at that point. Here's the basics of a Marx generator. First of all, we're charging, and you see everything's in parallel, so it charges everything up. You have your resistors. Then you set up a chain reaction where you set up that spark gap. Once that spark gap goes off, its conductivity increases, and then everything, all those resistors make it seem like, well, that's no longer the best path. The best path is now along these spark gaps. And you have that chain reaction where you have a huge spark and huge current flow at the end. So basically, you can charge up this Marx generator and get a huge voltage at the end. And this is sometimes used for feeding other things, though in and of itself, it can also cause some of the EMP effect, so I understand. Now, the diagram on this, I'm not sure I have right, because I've seen different versions of it in different constructions. But this is an explosively pumped flux compression generator. We're talking about you have to change the magnetic field really fast to induce a current. Well, that's what they're doing here. And instead of using nukes, they're using conventional explosives. So essentially, what we have here is what's known as a helical generator, and this is the best as I understand it. So we have it sitting there. We have a huge capacitor bank, maybe like a Marx generator or something. And when it peaks, well, let's go ahead and spark that. And when that peaks, at the same time, the electricity through that coil we have going around there, the solenoid, when it peaks, we want to set off the explosive. But we're kind of setting it off in a direction, like, you know, shaped charge kind of thing going on. So that goes down the tube, and this pushes the coil up against the outside of the tube, and it had a magnetic field on it, but now all of a sudden that magnetic field is getting shorted, and it's changing the shape of that wave. And you get that lovely EMP effect. And this is one of the ways people talk about constructing an E-bomb. Though I've seen different versions of the diagrams, I've seen antennas put on the front of this. I've also seen versions of this that basically use it as a feed source into something else, like, I think I'll have it up in a couple slides. There's other people who have been working on energy or directed energy weapons, like this is a HUF device. Sometimes you'll do a Google search for a homemade EMP weapon, which will actually show you as a HUF device, because it's not technically EMP, because it's not coming in a pulse. But you ever seen someone take a microwave apart and take its magnetron out and basically fry electronics by pointing it at them? Very similar effect. Not technically EMP, but it would be a type of HUF. There's people who have developed HUF systems for getting people out of an area. The idea is you hit them with these, I'm not sure microwave is quite what it's using, but hit some of these microwaves and it makes them feel very uncomfortable, heated up, get out of the way. You can also supposedly hit electronics with it and screw them up, though I haven't heard about a whole lot of our use of this particular active denial system on things other than humans. But that's an example, and like I said, some people have taken apart microwaves to do it. And there's also the Vindicator, which is a way of producing EMP, and you bring some kind of like high voltage, high current source, to my understanding, to the terminals there, and you can generate a big EMP effect through conventional, well, I shouldn't say conventional, but non-nuclear means. Then that brings us to geomagnetic storms. And sometimes people also get confused. I talk about, well, once the geomagnetic storm goes off, my radio is going to get fried. My understanding, as long as your radio doesn't have like huge antennas on it and it's not plugged into the power grid, the geomagnetic storm in itself won't take it out. Now, the geomagnetic storm, like I said, if you have it plugged into the wall, that might have overvoltage coming in. and your electric power grid may go out because long conductors and induced current in those could screw things up. Like I said, this is very similar to the E3 effect, but essentially a geomagnetic storm is caused by space weather. Let's say the sunspot on a solar flare causes a coronal mass injection. Not that I totally understand what that is precisely, but it causes problems to the Earth's magnetic field a little bit later. So you have kind of that effect where the Earth's magnetic field gets moved out of the way and maybe comes back in. And this has caused real-world effects in the past. Like, let's say 1859, there were supposed like telegraph systems, if I remember, who got screwed with and like set on fire because they had those long conductors, and it messed around with those. Now imagine if that happened to a modern-day system, because we have a whole lot more wires running around than we did back in 1859. Also, if you look in 1989, it's a little bit more current. The Hydro-Quebec's power grid was supposedly taken out by a geomagnetic field. At least that's my understanding what the explanation was for it. So it actually has happened in modern times. And while you wouldn't have the quick effects of like the E1 and E2, you could still screw up things and be completely non-nuclear and still be natural. Now that brings us to what types of tech will survive. And this is a thing where I have to say a lot of my understanding, or here's the best guidance I can find, or here's what the information I've read leads me to think, but it's hard to say. Radio waves, like I said before, do weird things. What will and won't survive depends on where it's at, whether or not it's plugged in, maybe how it was oriented, all sorts of things. But like I said, it can be unpredictable. So solid state in general is more sensitive. That'd be your things like your modern transistors, your diodes, things like that. I was looking around for solar panels and whether or not they'd be screwed up. My understanding is the little, what's the term for the diode on it that keeps it from becoming a load if there's no sunlight out? There's a little diode on it that when you're charging the batteries, it keeps it from becoming, the current from like flowing back if there's no light out. Well, that could possibly get fired, I suppose. But in general, solid state is more prone towards problems. What's known as thermionic technology, like vacuum tubes, is more resilient. I've heard tales of like Russian jets back in the Cold War still using vacuum tubes, in part because, well, probably because Russia didn't have as good a technology, I imagine, but also because supposedly it would survive EMP better. Though how truthful that statement is, I do not know. Also, there's certain problems with this. People say, well, I'm going to keep a bunch of vacuum tubes around so I can function after the bomb. Well, a buddy of mine who's a ham pointed out that you probably got to suck up a lot more energy using a vacuum tube-based radio, and try building something equivalent to a modern computer out of vacuum tubes. It ain't happening. So, power consumption and so forth. Now, fiber optics is an interesting thing. People talk about, bringing data in, because I talked about, let's say you have a completely shielded metal box that you have as your bunker. How you go get power in? How you go get data in? Well, fiber optic would be one thing for data because it's not conducting. It's conducting light, but not electricity. And shorter conductors are generally better because the less range over which you have to have that current come in, the better. Less area for it to actually, well, it'd be like the number of turns you have in a, to a degree, I suppose, number of turns you have in a transformer. If you don't have as much conductor there to induce a current into, you'll hopefully get less current. So shorter conductors are generally supposed to be better. As far as fry chart, and I got this from another FEMA document. Motors, my understanding, and transformers are generally going to be okay, although I've heard effects of E3 are supposed to be able to blow those out, well, at least the transformers, because you just have windings of metal, and generally it's fairly robust. Vacuum tubes, fairly robust. Transistors, though, and really small microchips, not as likely to survive, so understanding from FEMA resources. That brings us to surge protection. Let's say you have that shielded area off, but you got to power it somehow. I suppose you could, if you knew it was coming and you had everything battery powered inside, you could then shut off your outside connection. That would do the job, but that's probably not going to be practical. The question is, there's all sorts of surge protection out there already, and it's probably going to be capable of stopping that E2 effect I mentioned before, and I'm going to guess probably, well, I'm not sure about E3, but you have like fuses, like a lot of your surge protectors, like the one I blew out earlier today. I wasn't actually experimenting with a homebrew EMP weapon. I'll deny it to anybody who asks. Metal oxide varistors are used that once the current gets over to a certain spot, or the voltage gets to a certain spot, they become much more conductive, and they'll shunt current to ground. That's one of the common ways they construct surge protectors, along with a fuse inside of them. However, it takes a little bit of time before that blows, and before that metal oxide varistor will actually do its thing. But the effects of E1 can happen in 5 nanoseconds, thereabouts. I've seen different figures. Will that react fast enough? And I have seen charts that list like different types of metal oxide resistors, I think, in the same ballpark as far as how fast they'll react. But that's a huge issue there. I've also seen someone's diagram on how to build a EMP bunker. This is, I think, from a military website that shows something to keep the voltage spike from happening, where they basically have an isolation transformer. And I see the capacitor here. I'm still not sure what this component is. If anybody can tell me, well, find me a place on the line where you can see a diode that looks exactly like that. I'm still not sure what that symbol even represents. And I'm sure when people watch this on YouTube later on, we'll get a lot of comments. But the thing is, I got a lot of comments when I asked on Twitter, and a lot of them varied. Well, let's bring this, I think, the next diagram in a few bits. Another thing to think about is power sources. What's actually going to survive? This is so in need of further tests because I hadn't found, good information. We're talking about motors and transformers generally would be fairly survivable, especially if they're hooked off the grid so they're not get hit by E3. So traditional fossil fuel generators should keep functioning. The rest of the power grid, though, that's controlled by SCADA systems may have an issue, since the electronics that control the grid might not be there to help coordinate things. Hydroelectric, other than the SCADA system issue, water is going to keep flowing, so you can still produce things that way. Solar is interesting, but I was mentioning that diode before, and my understanding the way a solar panel works is also solid-state based. So I haven't found any hard information from what I would consider a reputable source on how reliable a solar panel would be. But if you want to keep energy afterwards, well, as Larry covered before, 1 is none and 2 is 1. Keep a spare. Wind should, I imagine, be fairly good. Well, I guess if you're close enough to a surface blast, it would screw up your system. But I'd have to imagine it would be fairly robust as far as the actual current generation. However, things like voltage regulators and so forth that actually turn that current into something you can use in the electronics you want to use it in might still be a problem. All right, let's talk about shielding. There's different ways of shielding it, but generally we'll talk about a Faraday cage. And I was going to bring this up as an example earlier, but now I actually can. I have a tag reader and writer on this device, and I have a tag here that I said I loaded up with various types of malicious content. It was detected, and it read it, and I can pull up the tag information. Well, the way a Faraday cage, named after Michael Faraday, though the concept's been around for a lot longer, supposedly Benjamin Franklin actually discovered the concept, is you have a conductive surface around the entire outside, and charges will instead move around the conductive this conductive substance and equalize, and whatever's inside of it doesn't actually get affected by the charge. And similarly, if you have, like, say, radio waves hitting it, the radio waves induce a current in it instead of what's inside, assuming you isolate some things, and you don't actually get the current induced in what's inside. So I've covered that with tinfoil, and back again. Now, I can't get it to read. I've also seen people make EMP bags that basically look like anti-static bags, though I'm assuming they're made of better material because the anti-static bags I've used, I could still read through them. So I suppose it depends on grade. But the idea is you have this huge metal shell around you that's maybe grounded, maybe not. It doesn't have to be grounded to be a Faraday cage, but my understanding it's a good idea. And whatever's inside of it should be safe from what's happening, with some exceptions there. The problem is, making one of these things and making it seamless, making sure there's no holes. Remember I was talking about directly getting into a device, not necessarily through an antenna or anything? Well, if there's any holes in it, that could be a bit of an issue. If it's not a continuous conductor the entire way around, like I mentioned, ammo cans. I haven't done a test on ammo can, but I could see the problem being, since you have that green paint all around the outside edge, you don't actually have a perfect conductor all the way around. Also, are there any holes in it? And there's different things for constructing these. I found different people talking about different gauges of mesh you should use to construct a Faraday cage, because let's face facts, making a completely metal cage that's all around you of a decent thickness gets expensive. So people have looked into just using mesh, which is a possibility. But I'm finding all sorts of varying information on how big that mesh has to be. It has to be significantly smaller than the wavelength of what you expect to hit it, which, as you saw, if EMP was all over the place. But I haven't got any hard set rules from a reputable source to say how small that mesh has to be. Like I said, you also have to have power coming into it. Let's say plumbing. All these things are other sources where the EMP effect could possibly get in because it got something induced on the outside. Also, for slow-moving magnetic fields, my understanding is a Faraday cage doesn't really do any good. For fast-moving magnetic fields, it'll reduce the current on the outside. For something slow-moving, let's say under 100 kilohertz, it's not really going to necessarily help you out. Then again, those materials like permalloy and mu metal, we're talking about magnetic permeability before. My understanding those are very magnetically permeable, and they don't so much stop the magnetic field as they move it around. However, if you're worried about Faraday shooting against an E1 or E2, my understanding, the part you're most worried about is the high frequency stuff, and anything slow moving is probably not going to be one of the things that's going to really affect your sensitive electronics. That's more of a worry for like power lines and large conductors. So I understand. Like here's a hypothetical room, and here's that little surge protector I mentioned before, which still has that icon. I need to figure out what that schematic symbol is. But you see they have a little airlock to come in, so they keep things sealed at all time. Your fiber optic for data coming in. They have an air cooling system, and I've actually seen things online about how to construct those of a certain size to keep certain wavelengths from getting through. I said I found all sorts of information on what size mesh you need, and nothing I found replicable. But I would say significantly smaller than the wavelength you're looking to stop. And another thing about these types of devices or these types of rooms is besides shielding from EMP, they're also interested because of Tempest. You may be familiar with Tempest? Tempest technology is essentially this. Your computer and other electronic devices are giving out electromagnetic waves, and whenever you just even type on your keyboard or do anything like that, if you analyze them in various ways, you can figure out what's going on inside a facility. So some places where they want to keep things really secret, they don't even know what people are typing on the keyboard. They don't want to have any worries about changing currents, possibly throwing radio waves out into the world and people being able to get signals intelligence from that. They'll put everything inside of a Faraday cage to keep basically radio waves from going out. So it has some double duty there. In my understanding, the professional built Faraday rooms that you can walk into, if you look at the door, it's not like the door just closes shut and there's a gap there. It's like something that's conductive that will kind of press together and make sure you have a better seal from an electrical sense. All right, improvised Faraday cage. And Larry already covered some of this stuff, but a microwave essentially is a Faraday cage on the inside of it for the particular type of wavelength that the microwave puts out. So in theory, you could throw something in a microwave, but once again, you're talking about a very wide range of frequencies. So I don't know if that's going to cover everything that you have to worry about. Filing cabinets are generally metal, though once again, that seal of where you close things is an issue. Ammo boxes, metal mailboxes, foil-wrapped containers, possibly anti-static bags, and of course there's a garbage can down there at the bottom. Like I said, I found various information. If anybody can find a hard set rule for what size the mesh has to be, I have found things that list like less than a tenth of the diameter of the wavelength. But like I said, that's a non-scientific wild-ass guess. That's what that stands for. All right, EMP tips and guidance. And the only guidance I can really give you besides, well, I'm going to repeat what Larry said here in a bit, I believe. Unplug your gear. That's especially important for the E3 component. If something doesn't ride in on there and destroy it. Disconnect antennas. And all of these I got from like military sources, what they recommend on a base. Disconnect antennas if you know it's coming, because that way it doesn't become a conductor to induce current into whatever devices you have that antenna hooked to. Have spares. That goes back to 1 is 0 and 2 is 1. Voltage clipping devices. This is like your surge protection and so forth. Though, like I said, I'd still like to see some more research on how fast one reacts and what will actually happen. The thing is, a lot of this stuff is kind of conjecture because, well, we haven't done those high altitude tests in a long time, at least not that I know of, at least not officially. I'm not in that ballpark, so I don't really know. Avoid large loops. I've even heard people talk about unspooling large wires so they don't become a little transformer. Shielding conduits and cables with, let's say, your natural shielding that you have around like any kind of coax, at least there's some protection. And bury lines, though I've heard people say to bury lines, and I've heard people say not to bury lines. The military source I found was recommending burying lines, so at this point, I'm going to recommend burying lines underneath the ground so it's a little less susceptible and get some shielding at least. Now, for those interested in doing some more research on this, there's all sorts of good stuff out there. There's the EMP Commission report, which has some information on testing, but not nearly as much as I'd want. And that's one of the more current things on it. The effects of nuclear weapons, chapter 11, is interesting for reading up on. I pulled some stuff from that, though I think the version I pulled up was from 1978. But I mean, the core physical effects we had a good handle on. I'm just not sure how well it tells us about all modern technology. FEMA has some information on this particular attack vector. Wikipedia has an EMP article, which was largely written by the guy I'm going to mention at the very end of this slide. So I understand, at least. Electromagnetic pulse threats in 2010. This, Mr. Miller was writing about, well, in part, non-nuclear EMP and how it could be used, and I found him useful when I was constructing my presentation. The electromagnetic bomb and weapon of mass destruction. A lot of stuff I have as far as my helical generator, that was from there. And I think as well as an E-house site I believe I visited. Early time E1 high altitude, let me see. I think these are supposed to be one particular thing. I found some more information on how hemp is supposed to be affected on a different gov site. And this future science page, if you want to learn a lot about the Fishbowl series of nuclear tests, this guy has tons of material out there. And I get the impression that the stuff he wrote for his own site was eventually put into Wikipedia, and he was doing a lot of article edits on that one. I generally try to stick with Gov and Mill sites, but his stuff mostly seemed to jive with what I was reading on Gov and Mill sites, so I decided to list him as well. Anyway, how far am I into this talk? How many hours am I at? Oh, shoot. Okay, yeah, we're way... all right, well, I'd like to say thanks to the conference organizers for having me, my buddies at DerbyCon and ISD Podcast, and the Open Icon Library for giving me some of the images. Finally, I'd like to invite everybody to DerbyCon next year. We'll announce the dates eventually. And for those who did make it this year, thank you much. And tell everybody else about it. We had a good time. And finally, if there are any questions, however, I'm already pushing the time limit beyond. So get with me sometime at the conference, and we'll discuss whatever you want to discuss. Have a good day.